Bridges age naturally, like humans. Heuristic forms of condition assessment of bridges may date back to the origins of structural engineering. However, the implementation of a strategy based on monitoring systems and data analysis to identify damage in real time at early stages has been defined as structural health monitoring, also known as SHM. SHM is a combination of words associated with the medical sector. Instead of looking for disease, we look for structural damage like scarring, cracks, and corrosion. The need of SHM has emerged with the construction boom after the World War II and with a relatively high number of bridge collapses observed around the world, like the Ince Ribeiro Bridge in Portugal, the I-35 bridge in the US, and the Morandi Bridge in Italy. SHM aims to save lives while supporting the minimization of costs with maintenance activities. The SHM is not meant to replace the traditional visual inspections. Like as humans go to the doctor once in a while, SHM intends to minimize the frequency of bridge inspections while increasing the knowledge about the structural condition. To deal with the large amounts of data and to perform the damage identification automatically, SHM has been cast in the context of a statistical pattern recognition paradigm, where machine learning plays an important role to learn the structural behavior from past data, following the same principle as the human brain. Deep learning is probably the most powerful technique nowadays.
In terms of sensing technology, we have observed developments moving from wire to fiber optic and wireless to non-contact sensors such as cameras and vibrometers. But today we also observe the emergence of promising chip technology capable to change the way we perform SHM. But how to bring such technology to the fingertips of practitioners worldwide? Practitioners need sound, robust, inexpensive, and hassle-free solutions that can give them answers in real time, meeting their needs as those needs arise.
With this in mind, we have developed App for SHM, a user-friendly smartphone solution for the structural health monitoring of bridges. Smartphones are light and convenient sensors that can retrieve data regarding the vibration of a bridge, just like guitar tuners feel the vibration of the string of a guitar. App for SHM extracts knowledge from this data and informs bridge owners on the condition of their bridge, sparing them the need for coding and heavy math.
You can think of sensors as the eyes, ears, and touch of SHM, as they allow us to see, hear, and feel the behavior of structures. On the one hand, they must be accurate and reliable enough so that we can trust their measurements. And on the other hand, they must be simple and cheap enough so they can become pervasive. You see, change can only occur if it can be performed with scale. Hence, Arduino-based sensor nodes, which include accelerometers as well as GPS modules for synchronization, have been our bet in the last years.
In SHM, having data from both damaged and undamaged conditions is essential for a sound damage diagnosis. This approach is very popular in those areas of engineering where prototypes can be damaged on purpose. But we can't do the same with our bridges. But a new idea has been floating around in recent years. Engineers have been using sophisticated software to build computational models of bridges called digital twins, which are then used to simulate damage scenarios that cannot be inflicted to real bridges. On a good day, this approach, called supervised learning, may enable engineers not only to distinguish between damaged and undamaged bridges, but also to identify the kind, location, and severity of damage.
Transfer learning is of tremendous interest for bridge SHM. The ability to solve new problems in terms of damage identification using prior knowledge present in the monitoring data, is based on human brain's ability to adapt previous experience to new situations. For instance, look at the Golden Gate Bridge in San Francisco and the 25 de Abril Bridge in Portugal. They do share the same structural system, the same material, and the same operation and environmental conditions. They were even built by the same construction company, which for sure optimized the designing of the 25 de Abril Bridge by transposing knowledge gained 3 decades before with the construction of the Golden Gate Bridge. So, the main idea of transfer learning is to reuse relevant knowledge from a known bridge, the source domain, to assess the structural integrity of another bridge, the target domain, with limited amount of monitoring datasets. This way, a robust classifier for a given bridge can be trained using datasets from other bridges.
We are not working in a void. We are fortunate to be part of a wide network of partners that give us motivation, recognition, and indeed funding. We are currently involved in national and international projects totalizing more than 4 million euros, in most of them as project leaders, supervise PhD students from 4 different countries, organize a European school in structural health monitoring, fully funded by the European Union, and we were happy to see our app for SHM smartphone application being selected as a finalist of the prestigious InnovaMais prize.
Recently, climate change has been posed as one of the greatest concerns for the health of bridges. Although the uncertainty associated with the magnitude of the change is large, the fact that our climate is changing is unequivocal, and so making bridges resilient to climate change is a priority for the authorities. An early adaptation may save lives and money. We have already set a roadmap for an integrated assessment approach for the adaptation of bridges to climate change, in which SHM is proposed as a mechanism for assessing continuously the structural condition and for triggering adaptation measures in a changing climate. We believe the key to success is to integrate adaptation into existing planning mechanisms and not to treat it like something new. With the Climate Bridge project, we came into conclusion that climate change should be a new dimension in the rehabilitation or retrofitting of bridges.
Standards and codes are important milestones to set a common SHM platform and to increase the transfer of knowledge and techniques to practical applications. Standardization may be the trigger we need to move SHM from research to practice. China has been one of the first countries in the world to implement a national code for SHM.
We have already identified 5 challenges for the future of SHM. Number 1. New technology and trends have unveiled new perspectives to observe the response data, but we still strive to obtain reliable information on the presence of damage. We need cheaper and better sensing technology. Number 2. As a multidisciplinary field, bridge SHM needs T-shaped civil engineers, where the vertical line represents deep knowledge in civil engineering and the horizontal line represents cross-discipline competencies and the ability to collaborate with professionals in other disciplines like electrical, computer science, and mechanical engineering. Number 3. Identifying applications where monitoring can have an impact. For instance, scarring has been responsible for 1/3 of bridge collapses around the world, so SHM should start from the foundations. Number 4. In the hierarchical structure of a damage identification, most research has been driven by incipient vibration-based damage detection methods. We must move from simplistic crack beam views to real problems in bridges. Number 5. Unless there are public domain examples showing a positive rate of return on investment, bridge SHM will continue at best to be one-off demonstration.